Welcome! In this session, we'll be tackling LeetCode problem number 1073, titled Adding Two Negabinary Numbers. This problem is a unique and interesting challenge as it deals with performing arithmetic operations in base -2, also known as Negabinary. We'll explore the problem statement, break it down step by step, and review an efficient approach to find the solution. Let's dive in. Let's continue. Let's continue. Let's continue. Let's continue. Let's continue. To solve the problem of adding two numbers in the Negabinary system, we first need to understand the unique properties of this base. Unlike the familiar base 10 or binary systems, Negabinary alternates powers of -2 for each digit position. This creates challenges when performing arithmetic directly. One straightforward approach to solving this problem is the brute force method, which involves directly converting the Negabinary arrays into their decimal equivalents, performing the addition in base 10, and then converting the result back to Negabinary. Specifically, we calculate the decimal value by summing each array element multiplied by its corresponding power of -2. Once the addition is done, we repeatedly divide the result by -2 to obtain the Negabinary representation. While this method is conceptually simple and easy to implement, it has some drawbacks. The multiple conversions between bases introduce computational overhead, especially for larger inputs, as the process requires iterating over the arrays multiple times. Although the time complexity is linear with respect to the input size, the additional steps involved in base conversion make this approach less efficient overall. A more efficient way to handle this problem is to simulate the addition directly in the Negabinary system, bypassing the need for base conversions altogether. This optimized approach makes use of the unique properties of Negabinary arithmetic. For instance, while the digits in Negabinary are still binary-like, the carries behave differently due to the negative base. When the sum of digits in a position exceeds 1, a carry is propagated to the next higher power, but the direction and value of this carry depend on the base of -2. To implement this approach, we start by initializing pointers at the ends of the input arrays and proceed with digit-by-digit addition, carefully resolving sums and propagating carries as needed. The resolved digits are appended to a result array, and any leading zeros are removed at the end. This method is efficient because it operates directly on the input arrays without intermediate conversions, making it well-suited for large inputs. However, it requires careful handling of carry propagation, which can be tricky to implement but is manageable with a systematic approach. Importantly, this strategy achieves a linear time complexity relative to the size of the inputs, ensuring scalability. Another potential approach to solving this problem involves using bit-level manipulation. Since Negabinary numbers resemble binary in some ways, low-level bitwise operations could theoretically be used to handle addition and carry propagation. This method may offer speed advantages for small inputs due to its direct interaction with the binary structure of the numbers. However, it introduces significant challenges, as implementing and debugging bit-level operations in the Negabinary system can quickly become complex and error-prone. Additionally, this approach is less readable and harder to scale in higher-level languages, making it impractical for more extensive applications. Ultimately, the optimized approach of simulating Negabinary addition was chosen as the preferred solution. It provides a balanced trade-off between efficiency and simplicity, avoiding the computational expense of base conversions while leveraging the system's unique properties. While slightly more complex than the brute force method, its linear complexity makes it highly effective for larger inputs. The bit-level method, on the other hand, was set aside due to its added implementation difficulty and limited usefulness in practical scenarios. To solve the problem of adding two Negabinary numbers, we first need to understand the Negabinary system itself. In base -2, each digit represents a power of -2. For instance, the Negabinary number 11010 evaluates to 16 - 8 plus 4, plus 0, -1, resulting in a final value of 11. Here, the digits can only be 0 or 1, but what makes this system unique is how carries and borrows work differently compared to base 10 or base 2. For the inputs, the problem provides two arrays, ARR1 and ARR2, where each represents a number in base -2. The least significant digit, or LSD, is at index 0. For example, if ARR1 is 1, 1, 0, 1, it corresponds to the Negabinary number -3. The first step in our algorithm is to align the arrays. If one array is shorter than the other, we pad it with zeros to make both arrays the same length. This ensures the addition process is straightforward. For example, if ARR1 is 1, 1, 0, 1, and ARR2 is 1, 0, we pad ARR2 to become 1, 0, 0, 0. Once the arrays are aligned, we perform the addition digit by digit. We initialize a carry variable set to 0 and traverse both arrays starting from the least significant digit. At each position, we calculate the sum of the corresponding digits from the two arrays along with the carry. Depending on the value of the sum, we adjust the current digit and update the carry. For example, if the sum equals 2, the digit is set to 0, and the carry becomes -1, because in base -2, adding 2 is equivalent to subtracting 2 and carrying over. Similarly, if the sum is 3, the digit becomes 1, and the carry is again -1. On the other hand, if the sum is -1, the digit is set to 1, and the carry becomes 1, as adding -1 in base -2 requires carrying over a 2. For all other sums, the digit is set to the sum directly, and the carry resets to 0. After processing all digits, we handle any remaining carry. If there is still a non-zero carry, we append it to the result and repeat the adjustment rules until the carry is fully resolved. Finally, we remove any leading zeros from the result, ensuring the output is compact. However, if the result is simply 0, it is returned as is, without removing the 0. The last step is to return the result. Since the addition process builds the result array in reverse order, we reverse it to match the required output format before returning it. There are a few key insights to keep in mind throughout the algorithm. First, the unique carry rules in the Negabinary system, where the carry can be -1 or 1, are essential for maintaining the validity of the digits. Second, padding the shorter array ensures uniformity during addition, making the logic simpler. Lastly, the iterative carry adjustment ensures that the Negabinary rules are strictly followed, even if the carry extends beyond the bounds of the input arrays. These steps together make the algorithm both efficient and correct. To implement this algorithm, we use three primary data structures. The input arrays represent the Negabinary numbers with their least significant digit at index 0, which simplifies the addition process. The result array stores the intermediate and final results of the addition. This array is built incrementally during the addition and reversed at the end before returning. Finally, the carry variable tracks the carry during the addition process, which can take values -1, 0, or 1 in base -2. When considering edge cases, we account for scenarios such as empty input arrays, which are treated as 0, and arrays of unequal lengths, which are padded with zeros for alignment. We also ensure that any final carry is fully resolved, even if it requires appending extra digits. Leading zeros are stripped from the result, except when the result is 0. For the time complexity, the algorithm processes each digit in the longer of the two arrays, leading to a complexity of O, max, n, m, where n and m are the lengths of the input arrays. The space complexity is also O, max, n, m, as the result array grows to accommodate the addition process. These considerations ensure that the solution is robust and efficient for all valid inputs. To solve the problem of adding two numbers in the Negabinary numeral system, we start by defining a Python class called solution and a method named addNegabinary. In order to simplify the addition process, the first step is to reverse both input arrays, ARR1 and ARR2, so that we can work from the least significant bit to the most significant bit. Next, we initialize an empty list called result, which will store the digits of our final answer, and a variable carry, which will track any overflow during the addition. Since the two input arrays may have different lengths, we determine the maximum length, n, to ensure we process all bits from both arrays. Then, we iterate through the range of this maximum length. For each index, we retrieve the corresponding digit from each array, defaulting to 0 if the index exceeds the array length. We calculate the sum of these two digits along with the carry. The current bit of the result is obtained by taking the modulo 2 of this sum, which we append to the result list. Finally, the carry is updated based on the rules of Negabinary arithmetic, specifically using the formula carry equals dash, total // 2. This ensures that the carry is correctly adjusted for the next iteration. If there is still a remaining carry after processing all bits from the input arrays, we continue handling it in a while loop. During each iteration, we append the current bit of the carry, calculated as carry %2, to the result. We then update the carry using the Negabinary rule, carry equals dash, carry //2, and repeat this process until the carry becomes 0. Once all the necessary bits are added, the result array, which was constructed in reverse order, is reversed back to restore the correct order of the Negabinary number. To ensure the result is properly formatted, we remove any leading zeros from the array. However, we make sure that at least one digit remains in the result, even if it's 0, to avoid returning an empty array. Finally, the modified result array is returned as the output. This implementation efficiently handles the addition of two Negabinary numbers and ensures the result adheres to the required format. Here, we start by defining the addNegabinary method, which takes two integer arrays, RR1 and RR2, representing numbers in Negabinary format. Since Negabinary addition is performed from the least significant bit to the most significant bit, we first reverse both arrays using the helper method reverse array. This ensures that we can process the digits in the correct order during addition. Next, we initialize an empty array list to store the result and a variable carry to handle any overflow during addition. We then determine the length of the longer array, n, so we can iterate through all the necessary digits. Inside the loop, we retrieve the current digits from each array, or use 0 if the index exceeds the array length. We calculate the sum of these digits along with the carry, then append the current bit, which is total %2, to the result list. Finally, we update the carry based on Negabinary rules, which differ from standard binary addition, as the carry is calculated as dash, total/2. After processing all the digits of the input arrays, we handle any remaining carry that might still exist. This is done by repeatedly adding the carry's current value modulo 2 to the result list and updating the carry as dash, carry/2, until the carry becomes 0. Then, we remove any leading zeros from the result to ensure the output is clean, but we also make sure at least one digit remains in the result to represent 0 correctly if needed. Once the result is finalized, we convert the array list into an integer array. To restore the correct order of digits, we reverse the result list back into its original format while transferring it to the final array. Finally, the method returns this properly formatted Negabinary sum. Additionally, the helper method reverse array is used earlier to reverse the input arrays and is defined at the end of this implementation. The reverse array method is a simple utility function for reversing an array in place. It uses a two-pointer approach, with one pointer starting at the beginning of the array, left, and the other at the end of the array, right. These pointers gradually move toward the center, swapping the elements at their respective positions on each iteration. The process continues until the left pointer meets or exceeds the right pointer, ensuring that all elements have been reversed. This efficient in-place reversal is crucial for preparing the input arrays for Negabinary addition, as it allows us to work with the least significant bits first without requiring additional space. Once the reversal is complete, the method returns control to the main program. In this example, we are adding two Negabinary numbers, 11111 and 101. To start, both arrays are reversed, though in this case, the reversal doesn't change their order. We then initialize an empty result array and set the carry to 0. In the first iteration, we take the first digits of both arrays, which are 1 and 1, and add them along with the carry, resulting in a total of 2. The least significant bit of this sum, total modulo 2, is 0, which we append to the result. The carry is updated to -1 because, in Negabinary, the carry is calculated as the negative of total divided by 2. Moving to the second iteration, we add the next digits, which are 1 and 0, along with the carry of -1. This gives a total of 0, so we append 0 to the result and reset the carry to 0. The result array at this stage is 0, 0. Continuing with the third iteration, we add the next digits from the arrays, which are both 1, along with the current carry of 0. The sum is 2, so we append 0 to the result and update the carry to -1. In the fourth iteration, we add the next digit from the first array, which is 1, while the second array has no corresponding digit, so we treat it as 0. Adding these with the carry of -1 results in a total of 0, so we append 0 to the result and reset the carry to 0. In the fifth and final iteration, we add the last digit from the first array, which is 1, again treating the second array's value as 0. With no carry, the total is 1, so we append 1 to the result. At this point, the result array is 0, 0, 0, 0, 1, and the carry is 0. Finally, we reverse the result array, which becomes 1, 0, 0, 0, 0, and remove any leading zeros if necessary. The output for this example is 1, 0, 0, 0, 0. In this second example, we add the numbers 1, 0, 1 and 1, 1, 1. After reversing both arrays, their order remains the same. We initialize an empty result array and set the carry to 0. In the first iteration, we add the first digits from both arrays, which are 1 and 1, along with the carry. The total is 2, so we append 0 to the result and set the carry to -1. In the second iteration, we add the next digits, 0 from the first array and 1 from the second array, along with the carry of -1. This gives a total of 0, so we append 0 to the result and reset the carry to 0. At this point, the result array is 0, 0. In the third iteration of this example, we add the last digits from both arrays, which are 1 and 1, along with the current carry of 0. The total is 2, so we append 0 to the result and update the carry to -1. After processing all digits, we handle the remaining carry. We append the least significant bit of the carry, which is 1, to the result. This reduces the carry to 0, so no further adjustments are needed. The result array is now 0, 0, 0, 1. Reversing this array gives 1, 0, 0, 0, and after removing leading zeros, the output for this example is 1, 0, 0, 0. In the final example, we add the numbers 1 and 1. Both arrays are reversed, but since they each contain only one element, their order remains the same. We initialize an empty result array and set the carry to 0. In the first iteration, we add the digits 1 and 1, along with the carry of 0. The total is 2, so we append 0 to the result and set the carry to -1. Once all digits are processed, we handle the carry. The least significant bit of the carry, which is 1, is appended to the result, reducing the carry to 1. We process the carry again, appending another 1 and reducing the carry to 0. The result array at this stage is 0, 1, 1. After reversing it, we get 1, 1, 0. Removing any leading zeros gives the final output of 1, 1, 0. The time complexity of the add-Negabinary function can be analyzed step by step. First, we reverse the input arrays RR1 and ARR2. Reversing an array takes linear time, so this step contributes O, len, RR1, plus len, RR2, to the overall complexity. Next, we iterate through the arrays. Here, the number of iterations is determined by the length of the longer array, which we denote as n equals max, len, RR1, len, RR2. Each iteration involves summing corresponding bits and handling the carry, which makes this step O, n. Finally, there's the processing of any remaining carry after the main loop. In the worst case, the carry might require additional iterations that grow logarithmically with the size of the input, leading to an O log n cost for this step. These three components form the foundation of the time complexity analysis. Following the processing of the main input arrays and the carry, we handle the result array. Reversing the result array also takes linear time, contributing O, n, where n is the length of the result. Additionally, we remove leading zeros from the result. This step involves a single pass over the array, which again costs O, n. To summarize the total time complexity, we sum all the steps. Reversing the input arrays contributes O, len, RR1, plus len, RR2, iterating through the arrays is O, n, processing the carry is O, log n, and handling the result adds another O, n. Since the logarithmic carry processing is dominated by the linear operations, the total time complexity simplifies to O, n, where n is the maximum length of the two input arrays. Now let's consider the space complexity of the add-Negabinary function. The input arrays, RR1 and ARR2, are stored in memory, but these are part of the input size and don't count toward auxiliary space usage. The result array is the primary contributor to space complexity. In the worst case, the result can be one bit longer than the larger input array due to carry propagation, requiring O, n, space where n equals max, len, RR1, len, RR2. The carry itself is stored as a single integer, which only uses constant space, or O1. Additionally, the temporary space used for reversing arrays and other operations is proportional to the input size but does not increase the asymptotic complexity. Therefore, the auxiliary space usage is dominated by the result array. When we combine all components, the total space complexity is O(n), where n is the maximum length of the input arrays. This is because the result array dominates the auxiliary space usage. Now, let's compare this optimized approach to a brute force method. A naive approach might involve converting the input arrays from Negabinary to decimal, performing addition, and then converting the result back to Negabinary. This process would require repeated multiplications and divisions, leading to a time complexity of O(n squared). In contrast, the optimized approach avoids this conversion and performs direct bitwise addition with carry handling, achieving a much more efficient O(n) time complexity. Moreover, the optimized approach maintains its efficiency across best, average, and worst cases, as the dominant operations remain the linear traversal of the arrays and the logarithmic carry processing. To mathematically justify the big O complexity, we let n equal max, len, arr1, len, arr2. Each operation, whether reversing the arrays, iterating through the bits, processing the carry, or handling the result, adds a complexity term of either O(n) or O log n. Since these terms are additive, the overall time complexity is dominated by the linear term, confirming it as O(n). Similarly, the space complexity is dominated by the result array, which grows linearly with the input size. No additional data structures are used, so the space complexity is also O(n). Together, this analysis solidifies the efficiency of the add-Negabinary function. When working with Negabinary addition, there are a few common mistakes to watch out for. First, incorrect carry calculation is a frequent issue. In base -2, the carry behaves differently because of the alternating powers of -2. Traditional binary carry logic does not account for negative values, so you must adjust the carry according to the unique properties of the base. For example, a carry of may first need to propagate 2 positions to the left, requiring specific adjustments. Next, forgetting to handle leading zeros can also cause problems. Negabinary results may include leading zeros, and failing to remove them could result in incorrect outputs or failed test cases. Ensure you strip these zeros from the result array, but remember that if the result itself is 0, the final output should be 0, not an empty array. Another mistake to avoid is misinterpreting the input format. Negabinary inputs are given as arrays of digits where the most significant bit comes first. If you treat the input as least significant bit first, you'll end up with incorrect results. Always confirm the input format and process the digits in the correct order. Now, let's look at a few more variations and tips to refine your approach. A common oversight is ignoring edge cases, such as when one or both input arrays are empty or contain only zeros. These scenarios can lead to runtime errors if not handled properly. To address this, add checks to handle cases where the input arrays are either 0 or empty. Another issue is implementing the solution inefficiently. Using overly complex or redundant steps to calculate the sum can increase time complexity unnecessarily. Instead, aim for an optimized approach that iterates through the arrays linearly and handles carry propagation efficiently. From an interview perspective, it's important to demonstrate a strong understanding of how Negabinary works, including the unique carry propagation rules. Be prepared to discuss this aspect in detail, as it's a common point of interest for interviewers. You should also highlight your ability to handle edge cases, such as inputs with varying lengths or large values, and explain how your solution achieves optimal time and space complexity. Specifically, aim for a complexity of O, max, n, m, for both time and space, where n and m are the lengths of the input arrays. Lastly, clearly articulate your carry propagation logic, as this demonstrates a solid understanding of the problem. Additionally, there are several related problems that can help you practice concepts similar to Negabinary addition. For example, LeetCode problem 67, add binary, involves adding numbers in base 2, requiring a similar understanding of non-decimal bases. Problem 989, add to array form of integer, focuses on array-based arithmetic, which is helpful for mastering digit-by-digit operations. Another relevant problem is LeetCode 371, sum of 2 integers, which challenges you to perform addition without using arithmetic operators, emphasizing bit manipulation techniques. Finally, LeetCode problem 2, add two numbers, deals with adding numbers represented as linked lists. The carry propagation logic in this problem is analogous to what's required for Negabinary addition, making it an excellent exercise to strengthen your understanding of carry handling. Finally, let's explore some alternative approaches to solving this problem. One option is to use simulated base conversion. You can convert both input arrays from base -2 to base 10, perform the addition in base 10, and then convert the result back to base -2. While this method is conceptually straightforward, it becomes inefficient for large inputs due to the repeated conversions and the challenges of handling large integers. A more optimal approach is to perform direct digit-by-digit addition in base -2, which includes managing carry propagation as you go. This method is efficient, with a time complexity of O, max, n agm, but it can be harder to implement due to the intricacies of Negabinary arithmetic. Another option is to use recursion for addition and carry handling. While recursion can be intuitive for small inputs, it risks stack overflow when dealing with large inputs, making it less practical in most scenarios. Weigh these trade-offs carefully to choose the approach that best balances simplicity and efficiency for your specific use case. Great job! To wrap up, we've summarized the key points from solving the adding two Negabinary numbers problem. We walked through the algorithm, discussed its time and space complexities, and highlighted the unique challenges of base -2 arithmetic. Remember, problems like this can deepen your understanding of unconventional number systems. Thanks for joining, and don't forget to like and subscribe for more coding tutorials. See you next time. That's the end of this tutorial. I hope you found this explanation helpful for understanding the solution to this LeetCode problem. If you enjoyed this content, please consider subscribing to the channel for more coding tutorials and solutions. Feel free to leave a like if this video helped you, and don't hesitate to comment with any questions you might have. Thanks for watching, and happy coding!